Welcome all of you. In the last two classes, we have been discussing entirely a different topic called multiple quantum transitions, multiple quantum NMR. And last class, we extensively discussed about the multiple quantum transitions detectable in 2-spin case and 3-spin case, especially double quantum and zero quantum in 2-spin case. And we came to know double quantum comes at some of the chemical shifts of the coupled spins, and since there is no passive spin, it is only a singlet. Similarly, in the case of zero quantum also, of the two coupled spins, there is no passive spin. Zero quantum comes at difference of the chemical shifts, and it could be, and since of course there is no passive spin, there is no J coupling. Now we also decided, we discussed about DQ and ZQ of three coupled spins, weakly coupled. We went to AMS case. There could be AM DQ and MX DQ or AX DQ. In each case, leftover spin is a passive spin. That can have a spin set alpha and beta and split this DQ into a doublet. And DQ comes at the sum of the chemical shifts, but the separation corresponds to, let us say, if there are two spins are active, it is sum of active and passive couplings. If it is AM double quantum, X is a passive spin, the separation corresponds to AX plus MX coupling. Similarly, you can work out for other double quantum. See, on the other hand, for zero quantum, there are three such possibilities. Zero quantum comes the difference of the chemical shifts, and separation corresponds to difference in the couplings, not sum. That is what we understood. And we took the example of how many barrier to higher quantum, how many transitions are detected when you go to fourth quantum, for example, 3-speed, triple quantum of 4-spin, double quantum of 4-spin, and how many such possibilities are there, everything we understood. And what is this apply? See, in the 3-spin case, only one is a passive spin. In the 4-spin case, two are passive spins. That is important thing. So you should understand each of them have two possible orientations. In principle, we have alpha alpha, alpha beta, beta alpha and beta beta orientations. 4 possible orientations for passive spins. And it can split into doublet, 4 line. In fact, doublet of doublet you should split. In fact, what will happen is, or let us say we get a doublet and measure the separation, and the separation corresponds to some of the active and passive couplings. So we understood those things, and we generated a formula. Using the formula, we found out how many peaks we can get for the mth quantum of n coupled spins. We found out, by taking the example of the 6 coupled spins, 6 single quantum transitions of 6 coupled spins gives 792 transitions. On the other hand, if you come to higher and higher quantum, for example, n-1 quantum gives only 12 transitions, n-2 gives rise to only 66 transitions. That is what we observed. As a consequence, as I said, higher we go, lower the number of transitions we get. The spectral complexity gets reduced a lot. And I also said n-1 and n-2 multiple quantum spectra are sufficient to get the complete information about the spectrum. So we don't need to go to analyze the complex single quantum spectrum with the redundancy in the transitions. So this is another approach. With that, we will continue further today to understand the pulse sequence of the multiple quantum detection. Okay, here is the pulse sequence for the multiple quantum detection. It is simply a simple echo sequence followed by a T1 and then the T2. See, 90 delta by 2, 180 delta by 2 is a echo sequence. It allows only coupling to evolve, refocuses any chemical shifts. No offset will be evolving, and refocus only, allows only coupling to evolve. We know that in the homonuclear case, spin echo will only refocus chemical shifts and coupling will evolve. So this generates antiphase magnetization, because we have observed that. And then the second 90-degree pulse converts this antiphase magnetization into multiple quantum coherences. Here MQs are generated in the T1 period. After the second pulse, MQs are generated. And after evolving for a time T1, the third 90-degree pulse converts this MQ into observable single quantum SQ. Here MQ will become SQ, and we are going to observe this. Here there is a echo. This is going to prevent chemical shift evolution. Only J will evolve. Here MQs will evolve, and here MQ will be converted to single quantum in the detection period, and that is what we are going to detect. So how do you interpret the double quantum single quantum correlation spectrum? for let us say 2 spin case. This is a double quantum dimension, this is a single quantum dimension. Detection dimension is single quantum. Indirect dimension is F1 is double quantum. So now I have 2 spins A and B. If 2 spins are coupled, where does it come? In the double quantum? It comes at some of the chemical shifts. That is what we have been observing. So here it comes at some of the chemical shifts. On the other hand, if you go to this DQ dimension, you get 2 peaks. I am sorry, single quantum dimension, you get 2 peaks. One at chemical shift of A and at the chemical shift of B. Only in the DQ dimension, you get some of these two. Only one. So if in this dimension, you have only one peak. Okay, if in this dimension, if you go, in principle, you get only one peak. If you take a projection here, you get only single peak. Here, if you get projection in this dimension, you get 2 peaks. One at the chemical sheet of A, one at the chemical sheet of B. That is what is happening. So F1 dimension gives you conventional SQ spectrum, and F2 dimension, and F1 dimension gives you DQ spectrum. The DQ of coupled spins A and B are correlated to single quantum. This is what is called DQ SQ correlation spectrum. Double quantum of 2 spins A and B are correlated to its single quantum spectrum. That is what you have to interpret. So the peaks in the SQ dimension shares a common frequency in the DQ dimension. What it means is, see for example, see here, for example in this case, this is the DQ dimension. In the DQ dimension, it shares, this DQ dimension shares common frequency. Both omega A and omega B, A and B will share a common frequency in this DQ dimension, in this F1 dimension. Okay. So in Cauchy cross multiplets are antiphase, especially cross peaks, and diagonal peaks are in phase. That is what we discussed. Whereas in the double quantum spectrum, the multiplet is antiphase only in F2. That is important thing. The value of the delta in the double quantum experiment affects how much of the here in this pulse sequence, value of the delta affects how much of the multiple quantum, okay, generated and its intensity. That depends upon how you set your delta. That defines about the intensity of the multiple quantum and its intensity. So general appearance of a MQ, especially DQ spectrum, is like this. Let us say I have a 2 couples case or 3 spin case A, B, C, or A omega 1, 2, 3. Now I am looking at the 1, 2 double quantum. So in the double quantum dimension, you get only one peak exactly at the center of this, which correspond to sum of, in this case let us say 1 and 3 is taken. So I will take 1 and 3 again. So this is 1 and 3 double quantum. It comes of chemical shift of 1 and 3. But it is not a single peak. You look at it in this dimension, it is a doublet. Why is this doublet coming? This doublet comes because of coupling of 1 with 2 and 3 with 2. It is a separation correspond to J12 and J23. That is a doublet. So in each case you can see here DQ dimension doublet, the sum of the chemical shifts of spin 1 and 3, or the sum of the chemical shift, it is a doublet. And the doublet separation correspond to J12 plus J23. That is what it is. Now go to the conventional single quantum dimension. At the center here, you take the projection, you get 4 peaks, because 1 is coupled to 2 and 3. But in the because of the DQ, what is happening is, it is a, you look at it, is doubly antiphase. You see, both of them are, they are doubly antiphase actually. So in the F1 peak, the doublet peaks are in phase with respect to coupling 1, 2 and 1, 3. But in the case of the F2, they are doubly antiphase. In the SQ dimension, they are doubly antiphase. So for example, peak for spin 1 in SQ dimension due to coupling 1, 3 is seen like this. This is coupling 1, 3 and this is 2, 3, and you will see this is 1, 3 coupling and this is also 1, 3 coupling. So it is going to be doubly antiphase. So the intensity of this peak strongly depends upon the coupling 2, 3. As the coupling strength keeps on decreasing, the intensity keeps on coming down. At exactly when it becomes 0, you will not see any peak at all. This can happen. If you don't see a peak in the double quantum dimension, it is maybe possible that the coupling of one of them, let us say 2-3 coupling, you are looking at 1-3 J coupling, double quantum, one of the coupling may be 2-3, maybe 0. You will not be able to see that. As a consequence, the intensity keeps coming down. As the J decreases, when J becomes 0 of the one of them, then you will not see the peak at all. So when J23 becomes small and when it is 0, peaks will completely disappear. So now multiple quantum, can we do all double quantum of a 3 spins at a time? Can we do all 0 quantum of all the of the 3 spins at a time? See, there are 2 spin double quantum and 2 spin 0 quantum I will take. I will consider AMX coupled case. I will take 2 spin double quantum and 2 spin 0 quantum. There are 3 such possibilities for each of them. Can I do at a time? Can I do individually? Of course it is possible. You can selectively have a AM double quantum and selectively have MX double quantum, selectively have JX double quantum. Similarly, you can have selectively AM, MX and AX 0 quantum also. Also you can have non-selective. You can do the experiment non-selective, all a double quantum can be simultaneously detected. That is also possible. So when the 3 spins are this thing involved, now 3 DQ can be simultaneously detected, AM DQ, AX DQ and MX DQ, and selectively you can also detect AM selective DQ, AX selective and MX selective DQ, all are possible. In each selective DQ, the remaining spin is the passive spin which is responsible for giving the doublet. Now very interesting application of this I am going to show you. Can we use this? Now we understood the idea about the double quantum comes at some of the chemical shift and some of the couplings with the passive, active and passive couplings, everything. That is what we discussed. In the, for example, in the 3 spin case, DQ comes at sum of chemical shift of 2 coupled spins and the separation is coupling between active spins and the passive spin. In the ZQ is the reverse, it comes at the difference and J also comes at the difference. Can you use this idea to get the relative sense of the coupling? We can see that. The spectrum, how does it look if I have a positive J value and the negative J value? This we discussed this extensively in the first course. How does the spectrum look? 1D NMR spectrum when the J coupling is positive or negative. For example, this is a J is positive case, I am considering AX case. AX spin, there are each one will give rise to a doublet, you know that. In the AX case, AX to weakly coupled spins case, A will give a doublet and X gives a doublet. Fine. Now what happens if I measure the J coupling, this is the center gives a chemical shift. Now I do not know whether J is positive or negative. Assume this is J is positive. Now what happens to the spectrum if J is negative? Can you see the difference between this and this? Absolutely no visible difference at all. But something internally happens. Look at this A2 became here, this A1 came here. The peaks just got reversed, they interchanged. Similarly X1 and X2 got interchanged. So when the sign of the coupling changes, only peak positions just gets interchanged. As far as the total appearance of the spectrum is concerned, it remains unaltered. The appearance of the spectrum is invariant with the change in the sign of the coupling. This is what happens. So it means you cannot get the sign of the coupling from the conventional one dimensional NMR spectrum. Now is a practical example I am showing you. This was the NMR spectrum of 3 protons. This forms a weakly coupled AMX like this. We are getting 12 peaks, 4, 4, 4 for AM and X. Now can I get the relative signs from this coupling? From 1D spectrum it is not possible. Let me use multiple quantum and see. Now in the AMX spin system we have 3 DQ, 3 ZQ. It could be AM double quantum and 0 quantum, AX double quantum and 0 quantum, MX double quantum and 0 quantum. All the 3 are possible. In each case the excited spins are the active spin and the third spin is the passive spin. So in AMS case X is passive, AX case M is passive, MS case A is passive. So we must get doublets for both DQ and ZQ. Once sum of the couplings, other ZQ case it is difference of the couplings. That is what, with that idea an experiment was done. This was a homonuclear non-selective DQ. That means at a time all the 3 double quantum are detected. There is a J coupling. Look at this one. This is a AM double quantum, it is a doublet. This is a MX double quantum, it is a doublet. This is a AX double quantum, it is a singlet. How is it possible? I told you, when there is a AX double quantum, M is a passive spin. This must be a doublet because of J AM plus J MX. That should be a doublet, but I am not seeing a doublet, I am seeing a singlet. Whereas here and here I am seeing doublet. The couplings are different, strengths are coupling are different, as a consequence the separations are different. But here there is only a singlet. What does it mean? Why is it not a doublet? Let us try to answer it. Before that, I will tell you something about spin state selective detection. What is spin state selective detection? Look at the molecule like this. I am going to look at CA3 peak in this hypothetical molecule. How many peaks you expect? CA3 is coupled to CH2. What will happen? It will become a triplet. CA3, I am detecting CA3, observing CA3, it will split into triplet because of CH2. What will happen to triplet? Each layer of the triplet will split into a doublet because of CH proton. It is split into a doublet. As a consequence, you are going to get triplet of doublets. That is what you are going to get. And what are these components of triplets of doublet? These all correspond to alpha 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 state of CH proton. These all correspond to beta 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 states of CH proton. Now, my question is, you can measure this and get the J couplings. Now, high field and low field component, this is a high field component, this is a low field components. Can I separate it out is my question. If I separated high field and low field components, or instead of separation, if I can detect only beta 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 peaks and suppress alpha 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 peaks, that is also fine. Either way, I can do detect only one of the components, alpha 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 peaks or beta 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 peaks, or I can separate them physically, spectroscopically. Can I do that? This one, or I can get this one. In which case, I can drastically simplify the spectrum. This is called spin state selective detection. The spin state selective MQSA correlation in the homonuclear case we will understand now with the knowledge of what is a spin state selection. See, when you apply a mixing pulse, third pulse or second pulse in the pulse sequence given, and an isolated coupled spins, the passive spins are the remaining homonuclear spins. It leaves alpha and beta states of passive spins remains unaltered. See, what we do is, let us say I am taking at the AM double quantum. I selectively detect AM quantum, AM double quantum. I do not touch X at all. I do AM double quantum, I do not touch X at all. Then what will happen? The spin states of the passive spin X remains unaltered in both MQ and SQ dimension. Alpha beta remains same. Same thing true for any double quantum you consider. Take MX double quantum, A is a passive spin, A has alpha beta states. So, MX double quantum, what will happen? Then in the MX double quantum, again in both MQ dimension and SQ dimension, A spin, alpha and beta states remains undisturbed. This is called spin state selective detection. This gives rise to what is called spin state selective detection. Please understand that. Okay, this is what it gives rise. This is for the homonuclear case. What happens if it is a heteronuclear case? That is a different question. I will come to that later. There, it is a different way. Now, I will look at the AM spin selective DQXQ spectrum of AMX. Fantastic. It is expanded region. This is AM double quantum. So, in the single quantum dimension I will get A and M chemical shift. In the double quantum, what you will get? Sum of delta A and delta M, and it is a doublet because of splitting with X, alpha X and beta X. Perfect, no doubt about it. Now, what is the separation gives? J AX plus J MX. That is what I am going to get it. We measure it, let us say. That is what the spectrum is. So, an interesting thing will happen when there is a spin state selective detection like this. I take the cross section of each of them here and plot out separately like this. Take this cross section and plot here, this cross section and plot here. Then there is a displacement here. That displacement gives me one coupling and this separation gives me one coupling here. This displacement gives me MX coupling, this separation gives me AM coupling. So, very easily we can get this one, and sum here gives you AX plus MX. So, SQ dimension provides active coupling to AM, and a displacement of cross sections provide corresponding passive coupling at each chemical shift. That is what happens. Now, we have taken the cross section of each of them, and now what is happening is it has removed the redundancy. Instead of 8 peaks, I do not need to worry, I get only 4 peaks here, that is enough for me. It removed redundancy of the transitions, and that also separated active and passive coupling. How did it separate out? Look at this here, it separated active and passive coupling. Here these are the active couplings, and the passive coupling MX is separated out here. See, from the displacement you can get the passive couplings, and also the direction of the displacement gives me the relative signs of the coupling. See, both are tilting towards the right. So, this and this, if you consider, it tilted towards the right. Similarly, if you consider this and this, it is tilted towards the right. But both are tilted in the same direction. That means the relative signs of this coupling and this coupling. Here you must understand one important thing here. In this case, what you are going to get is MX coupling here. Here you are going to get MX coupling, you are going to get AX coupling. And now both are tilted in the same direction. What does it tells me? The passive couplings MX and AX have the same sign. If the tilting were opposite like this, then we can say they are opposite in signs. The coupling constants are opposite, but now they are tilted in the same direction. It tells me the coupling MX and JX are same sign. I do not know what is the relative absolute sign. I can talk about the relative signs. If this is negative, this is also negative. If this is positive, this is also positive. So, it is only relatively both of them have the same sign. Absolute sign I do not know, because the direction of the tilting is identical. The slope of the displacement vector gives me relative signs of the passive coupling. So, it means JAX and MX have the same signs. Fine, we have got one knowledge. Now, we will go to MX spin selective DQSQ. When I do the MX selective DQSQ, very interesting thing, I am doing MX. Now, what is the passive spin? A. So, what are the passive couplings here? AX and AM. In the this is double quantum dimension, the tilt of the displacement we have taken. Now, alpha and beta component gets separated out because of the spin state selection. I can get this correspond to alpha spin state, this correspond to beta spin state. Fine, these are the two cross sections, but look at the cross section, this is tilted this way, this is tilted this way. What does it mean? The passive couplings AM and AX are opposite in sign. This is what I am going to tell you. These are the passive couplings, these two passive couplings here, AM and AX are opposite in sign. Earlier both were similar sign. Now, use this logic. The tilt of the displacement will say when they are opposite. Now, confirm that by doing 0 quantum. When you do the 0 quantum, what will happen? See, look at this one, this separation is smaller, MX 0 quantum, double quantum. On the other hand, when I do MX 0 quantum, the separation increased. How can it happen? I have been always telling you 0 quantum evolves as the difference of the couplings. But if there was a difference, then I should have reduced further. The separation should have become smaller. Instead of 10 minus 8 if I take, this should have become 2. In the double quantum it will become 10 plus 8, it will become 18 hertz. Here it is only, it should become 2 hertz. But on the other hand it has become more than the double quantum. How it can happen? This can happen only when one of the coupling is negative. That is what we observed. One of the coupling, if it is negative, because of opposite sign mx and ax, which are opposite in sign, instead of subtracting they are adding up. This is the reason why separation becomes larger. So now whatever we observed in the double quantum, we are confirmed with the zero quantum, and we say these two signs am and ax are, and am and ax, I am sorry, mx and ax are opposite in signs. So we can find out am selective zq we can do. Again you can see these two are I am sorry, tilted in the same direction. This tells me mx and ax have the same sign. Okay. So spin state selective detection, because of this, now what we did is we go back and then use this logic and find out in this non-selective case we saw the spectrum, here. Why it is a doublet? Now it is a AX double quantum. So AM and MX, AM and MX are the couplings. Now they must be opposite in sign. Look at it, AM and MX. They are nearly equal strength, 11.2 and minus 10. Approximately they are coming closer. That is the reason why they are nullifying. The separation reduced or almost coming close to 0. That is why it appears like a singlet, because the signs are opposite. So we could find out the relative signs of the coupling by using selective detection of double quantum in this case. So now we will go to another example of a spin state selection in a heteronuclear spin system. What happens if I see the heteronuclear case? Heteronuclear case, you do not have to do selective excitation. Simply non-selective excitation of homonuclear spins you do. The heteronuclear spin which is present, it will not be disturbed at all. We do not touch it at all. Then that spin state remains unaltered both in the multiple quantum dimension and also in the single quantum dimension. That pertains to spin state selection of the heteronuclear spin. So that is the idea. So it gives rise to spin state because the spin state of the passive heteronuclei remains unaltered. We took the look at the example of this one. It is a 1 chlorobenzene. Now I am looking at the fourth quantum of 4 protons here. Now what is the passive spin here? Passive spin is fluorine. When I do the fourth quantum, now I am numbering it as 3, 4, 5 and 6. Fourth quantum will give me a single peak. All 4 protons are simultaneously flipping from alpha 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 to beta beta beta. Now this is passive spin splits that singlet into a doublet. Fine. So this is a doublet. What is the separation of this doublet? Correspond to 3 4 2 3 2 4 2 5 and 2 6 couplings. Okay. Coupling of this fluorine with all the 3 protons together gives rise to the separation. You measure that, it turns out to be this value, and then you can find out the direction of the displacement also. Look at it, this is in this direction, this is in this direction, whereas this is in the opposite direction. So measure the coupling from the displacement vectors and find out if all the 3 are positive, this is negative. If all the 3 are negative, this is positive. You can get the relative sign of the coupling here. Same way in the other ring also, in the other one you can find out this is negative this direction, this is like this direction, whereas this is in the opposite direction. This is for a different molecule. So you understand, this is how we can find out relative signs of the coupling between proton and any other heteronuclear spin. Okay. So this is a simple example in a pyridine. If you consider now 2 fluoropyridine, fluorine is heteronuclear spin. Do the fourth quantum of pyridine here. You have got 4 protons in the single quantum dimension. In the double quantum dimension, you can see this is tilted this way, this is tilted this way, whereas these two are tilted this way. Say sign of these two couplings, heteronuclear coupling, that is 4 and 5, sign of this proton 4 and 5 with fluorine are opposite in sign compared to sign of 3 and 6 couplings with fluorine. This what you can get the information about sign of FH couplings between that is heteronuclear couplings by doing the homonuclear non-selective excitation of the highest quantum available here. So, spin system filtering I will take in the next class. I will discuss that in the next class, spin system filtering, and then that will be just for 15-20 minutes. I do not know, I will try to cover it faster. Then we will go to a different topic, altogether a different topic. So far we were discussing about the solution state NMR and the techniques we adopt in solution state NMR and what in the solid state NMR are slightly different, and the interaction parameters are present in solids are different than in liquids. But then how to get a liquid like spectrum in case of solid is a different methodology is there. So, we will discuss solid state also later. So, in the next class I as much as possible I will try to cover, if not does not matter, in the remaining period we will have enough time to discuss solid state NMR. But what I was trying to tell you so far is the multiple quantum NMR, varieties of things we discussed. One of the utility we saw in this class about detection of the determination of the relative signs of the coupling. We took the example of 3 coupled spins. You can have a non-selective excitation of all the 3 double quantum AM, AX and MX, or non-selective excitation of or selective excitation of 3 zero quantum, or non-selective excitation of all the 3 at a time also possible, both double quantum and zero quantum. And we observed very interestingly, depending upon the splitting separations in the dq dimension and zq dimension, because of the coupling between the active spin and the passive spins, we measured the separation and we understood what is the relative sign of the coupling. That can be confirmed, what you detected from the dq was confirmed from the zq also. That is a very interesting thing we observed. So, the relative sign of the coupling we could get by using multiple quantum NMR. So, how we do multiple quantum NMR also, I showed you a simple 3-pulse experiment for homonuclear case, where we have a echo sequence to prevent the chemical shift evolution, and only J couplings will evolve, and then the second pulse convert into multiple quantum, and the last pulse convert the antiphase coherence into detectable coherence. That is what we are going to detect. And the spectrum represented as a multiple quantum to single quantum correlation spectrum. If it is a double quantum, it is a DQSP correlation. If it is a fourth quantum, it is a 4QSP correlation. If it is a triple quantum, it is 3QSP correlation, like that. In the indirect dimension is highest quantum, and direct dimension is the single quantum. That is what we discussed today. So, I will stop here. In the next class I will try to discuss about the spin system filtering, one more important application, and then we will switch over to altogether a different topic, solid state NMR. So, thank you very much.